a bit. So if you remember all this stuff about transformations, you might not need to write a ton of notes down. But you're going to have some questions on your test talking about describe the transformation that's happening. Maybe make a graph based on the equation. And knowing transformations just makes graphing so much quicker and so much easier to do. So that's why I think that you should know these, should learn them. So I kind of wrote out like what's happening in a generic equation, and then I'm going to write the real equation next to it. So if you feel really good about most of this, you don't need to write it all down. I'm okay with that too. But this is just some really good notes in case you don't remember all of it. Thursday. Oh wait, I think they're on the field trip. So remember that if your number is added, I'm actually going to just show you both. You could just put plus or minus one. But if a number is added or subtracted outside of a function, that just takes that function and moves it up or down vertically. It doesn't change the shape of it. And so I'm just going to kind of give you some examples of different functions. So if I wrote like f of x equals x squared plus 7, right? That's a vertical shift up 7. Or if I wrote the absolute value of x minus 3, that would take that v-shaped absolute value and just move it down 3. So adding and subtracting for any function outside of the function is always going to give you a vertical shift. So vertical shift is on the outside. Horizontal shift is on the inside. So again, horizontal shift, C units to the right or the left. Give me a minute, and then we'll write some examples. Stretches and shrinks, I think, are the hardest ones, but inside a function. So that means like inside the squared part, inside the absolute value, inside the square root. So like I could say g of x equals the square root of x minus 3. What was it? Remember that it's the opposite of what you probably think it should be. Like moving to the right is actually subtracting. So that means it would move it over right on the x-axis. Or I could say x plus 4 cubed. I'll take that cubic graph and just move it to the left 4 units. So knowing that saves a lot of time. When I taught Algebra 2, I always told them, worst case, you just make an XY chart. No big deal. When we have a test, there'll be some questions asking you to describe the transformation, which again, you could just graph it and see what happened, but it's going to be a lot quicker if you know these transformations. So I kind of stressed that a lot more than I did when I taught Algebra 2. We can also talk about what a negative does to your graph, and I always say you know this already, especially thinking about quadratics. If the x squared is negative, you know that that flips it over. So we can talk about putting a negative inside or outside a function is going to reflect it in one axis or the other. So that's my next one, I think. Are you okay with this? Oh wait, just kidding. We're going to do examples first. I'm not going to give you awful things to graph, but I just want you to know how to take the parent graph, that's what I called all those 10 graphs that we wrote out, and graph these. So I'm going to make the f of like the original graph on mine. So I'm going to say f of x equals x squared. I'm going to graph that, and then I'm going to graph the translation just so you can kind of see that it's the same shape. If you feel really good about this, you might not need to do that. But I think it's helpful to see that it's the same shape. We're just moving it over. So x squared. Hopefully, those 10 graphs, you can graph them really easily. You know that x squared starts at transformations to graph is that you know those parent graphs. So you know what that looks like. Because if you know that, what's happening here? X squared minus 3. What's happening with this graph? It's moving which way? Down 3, which means theoretically, if you had a magic smartboard on your notebook there, you could just take this graph and you could just move it down. I don't know if mine's working on. Ooh, maybe. You could just move it down. Oh, because I went over it. You can move it down 3 units and it's the same shape. But what you have to do is you have to just say, oh, I'm going to go down 3 and it's the same shape. So if I go over 1, I go up 1. If I go over 2, I go up 4. And then I don't have to make an XY chart. I don't have to plug numbers in. I just know the shape, and I moved it down 3. So what's happening in number 2 here? What's the shift? Up 1, left 2. So again, I'm not going to graph the original on this one. If I know the shape, then I'm going to go up 1 and left 2, or left 2 and up 1. Either way, I'm going to start with where that normally 0, 0 point is. That's how I do it. And then I know when I go left and right, I go up 1. And when I go over 2, I go up 4. Anything else? That looks so terrible. That was when you hand draw the points. Sort of like that. My points are spaced out more on that one than that one, so it looks bigger. Do you agree with that? Oh, I went up too many. Did I go up too many? No, that's right. Your silence makes me think I'm wrong. They're not just going to be parabolas. They could be absolute value graphs. They could be the cube, which is like the little S shape. They could be lots of different things of those 10 graphs that we did, but this is the idea of it. All right, reflections. Again, if you ever forget this, you can pick a couple points and see what happens here. I always feel like the reflection on the x-axis you have drilled in your head because of quadratics. Does it open up or does it open down from algebra 1 class? But if you have a negative on the outside, that means your y values are changing. So x stays the same, but y is changing. And so I kind of did an example here. Y equals the absolute value of x. Or if you put a negative out front, then now all of your y values are going to be negative because you still plug in the same x values, but you now get negative numbers. And so that means that V shape is just going to flip over. So again, I'll just draw both of these. So if I draw this one, I'm not going to make points out of it. I'm going to just draw it like that. And say that's y equals absolute value of x. And if I plug the negative in, I'm still going to get 0, 0, but now all my y values are going to be negative. It's probably the one we see more often in functions. But we can also have a reflection in the y-axis, and again, it's all about whether it's on the inside or the outside of the function. So in the x-axis, it's all about the negative being on the outside. If it's a reflection in the y-axis, it's all about the negative being inside the function. So the negative is inside. So I wrote h of x equals f of negative x. And so I think, I don't know what I did here. Oh, I did a square root one because you actually can see that it's different. So this square root symbol is not over the 2. I'm going to write that out. think about y equals x squared. If you plug a negative inside that and you square those numbers, you get the same thing because it's already reflected. So they give the same graph. Nothing really changes. But if you pick something like this, notice I threw an extra thing in there, not just a reflection, but I threw also a vertical shift in this. So let's just kind of think about picking numbers for this. If I'm going to graph a square root function, I always pick perfect squares, things that will make that a perfect square. If you don't know the shape of it, you can still make a chart. Hopefully you know that it kind of goes out like this, but maybe you need a little chart to help you. So if I was going to graph this, I'm going to pick 0. Why am I going to pick 0? It's the start of my domain, right? I can't plug any number smaller than 0 in that. And if I plug 0 in there, I just get 2. We'll kind of forget that 1's a perfect square, but I'm going to pick 1 also. And always on a square root function, if you plug in 1, you get 1, but there's this vertical shift here, so that's why we're moving up 2. So 1 plus 2 is 3. And then the next perfect square is 4. 2 plus 2 is 4. And that's how the square root function always goes if there's no stretch or shrink there. Wherever it starts, and then it just goes up by 1, because the square root of 1 is 1, the square root of 4 is 2. But because it's up 2, that's why these numbers are up 2. And again, always resort to those XY charts if you need them. But on this one, it would be up at 2, and then it just goes up by 1 from there. And know that shape, that it's like a half of a parabola. It should be curved. So notice what happens when we throw that negative underneath that radical. If you were going to make an XY chart, we can still pick 0 because negative 0 is still 0, and you still get 2, but you can't pick the same X values anymore. You can't pick 1 because you would get negative 1 under the radical, and that's an imaginary number. So the X values are actually going to change now. Like you have to pick negative values now to get the same Y values. Your domain has changed. Now instead of starting at 0 and going up, it starts at 0 plus negative infinity up to 0. So that's what I mean by the X values change. But you still get the same numbers over here now, right? So if you change your X values, if I plug in negative 4, I still get positive 4. So it just flips over. Let me change colors here. So I'm just going to go like this. It's the same graph, it just flips over. That's why if you know the transformations, if you know what's happening, my graph doesn't look the same, then you don't have to pick the points every time. Okay? Alright, it's up to you if you want to write all this down. I definitely want you to write the rules underneath this. But just so you know, everything we've talked about up until now, the shape hadn't changed, right? We've just moved it left, right, up, or down, reflected it. It was the exact same shape. Alright, those are called rigid transformations. I imagine that being because the shape stays the same. The shape doesn't change. But when you do a dilation, that's what you call them in geometry class, or we call them stretches and shrinks, or stretch or compression. When you do that, it actually changes the shape. All right, so those are called non-rigid transformations, and the rules are all about if you're multiplying by a number inside or outside. So again, I just like to give you that information. This is the part that I would say I really think you should write down, the stretch and shrink stuff. And I do want to caution you that this book writes it differently than the Algebra 2 book in terms of how they do the horizontal one, and so I want to make sure that we kind of think about that as we do this. So the big thing I want you to get from this is vertical is when the number's outside the function. All right, so a vertical stretch, stretch it out like this. A vertical shrink is going to kind of compress it down like that. That's when the number's outside. How do you know if it's a stretch or a shrink? It's all about whether the number is bigger than 1 or less than 1. So if the number is bigger than 1, then that's when it's stretched out. Like y equals 2x squared. So the 2 is not in the squared part, and that's going to stretch that parabola by a factor of 2. If the number out front is less than 1, and by less than 1 I don't mean a negative number, basically I mean between 0 and 1, because a negative means a reflection, right? Negative has nothing to do with stretch or shrink. If it's between 0 and 1, then that's going to shrink it down or compress it down. So that would be like, I don't know, 1/4 times the absolute value of x. Try not to use x squared every time. Outside means vertical, and I think it kind of makes sense that if it's a bigger number, it's stretching it. If it's a fraction, it's compressing it down. It's like 1/4 the size. And we'll talk about how we can do this without have to always making an XY chart, but definitely XY chart's okay on this. Horizontal stretch and shrink is a little bit different, and especially the way this book writes it. Like the Algebra 2 book always just still used the C, and then like the rules changed on whether it was greater than or less than. But this book likes to write it as a fraction, so let me give you a minute to write this. This is saying f of x over c, right? So they're putting c in the denominator. Just make sure I always stress that I write this wrong. And then I'll talk about maybe we can find a better way to think of this than memorizing this exact rule. One big thing I hope that you see is vertical, the numbers on the outside, horizontal, the numbers on the inside. And it's going to look like the stretch is when it's a smaller number, the shrink is when it's a bigger number, and I'll show you what I mean by that by an example. So a horizontal stretch is when it's on the inside, like if I said y equals the square root of x over 7. That's ugly. That'd be a terrible graph. Notice that the 7 is in there, but I really did pick a value where c is greater than 1, because 7 is greater than 1, but it looks like it's a fraction. So like the Algebra 2 book would say it's a horizontal stretch when it's f of cx, or I don't know, when c is less than, I don't know. It's just like the opposite of what the Algebra 2 book says, which is, I think, kind of annoying. But if it looks like it's a fraction, less than 1, then that's when it's going to be a stretch. And a shrink, what if I picked a fraction for this? Like y equals, I'm going to show some work here, x over 1/2 squared, right? That would be picking a value less than 1. The book's never going to leave a problem like that. What is x divided by 1/2 actually simplify to? Dividing by a fraction is the same as multiplying by reciprocal. So that's really going to look like this. Right? So when you divide by a fraction, it's not going to be a fraction anymore. It's going to be this. So that's why I think the book is kind of confusing and kind of lenient when it comes to stretches and shrinks. But what I really want you to know is the difference between vertical and horizontal, okay? When you actually graph it, you'll know whether it's a stretch or a shrink. I want you to know vertical means on the outside, horizontal means on the inside. That's kind of my big thing that I really want you to know from that. There's even times we can argue that a vertical stretch could be the same as a horizontal shrink. Like if I gave you a graph and asked you to say what's happening, depending on how you look at it, you could write it the same way depending on the graph. So just be aware, vertical stretch is when it's on the outside, horizontal is when it's on the inside, and it's going to change the shape of the graph. So let's see if we can do a couple of these, and I think that's it for my notes, which is a good thing, right? Some people always go back to XY charts with stretches and shrinks because they know the shape is changing, and that's okay. I just want to talk to you today about if you don't want to make an XY chart every time, how you can use this. If you know what the original graph looks like, you can still do this one without always making an XY chart. Again, I'm going to graph the absolute value of x, at least on this one, so you can kind of see what that looks like. Since the number's outside here, is that vertical or horizontal? Yeah, and then since that number's bigger than 1, I can even say I know it's a vertical stretch, which means that graph, that V shape should look like it's kind of stretched out. It's going to look skinnier. Absolute value is V function, starts at 0, 0, and normally we go up just one at a time, right? So it's just going to look like this and like this, sort of. That's why I should make points, because it's off. Okay, that's f of x. If you're stretching that by a factor of 2, it means every point you normally get, you're now multiplying by 2. So normally you get 0 when you plug in 0. 0 times 2 is still 0, so that's why it's still at 0, 0. But now when you plug 1 in, right, you normally just get 1, but now you're multiplying that by 2. So when you plug 1 in, you now get 2. When you plug 2 in, you're doubling that. Normally you got 2, now you're getting 4. Right? So if there was a 3 in front of it, everything's tripling. If there was a 7 in front of it, everything's multiplying by 7. That's going to be really skinny. So on this side, it's the same thing, right? When I plug in 2, I get 4. So we've taken that and we've stretched it out by a factor of 2. That's why if you put a fraction in front of this, it compresses it or it shrinks it, because you're taking everything by a half now. So when you plug in 1, you get a half. You plug in 2, you get 1. So it's taking everything and making it compressed more. Make the XY chart if you need to. I just wanted to kind of show you that. Negative 1/3 absolute value of x. That's kind of terrible, right? Negative 1/3 absolute value. What is that negative going to do to my graph? Yeah, that's going to be a reflection. It's going to flip it over the x-axis. So which means I don't really need these points up here, but that's okay. So we could, again, I'm going to make this same graph here. Normally, this is my parent graph. Because this is less than 1, this should be a vertical shrink. And we could still say 0, 0. So here's where you have some options. We could plug 1 in here, and we're going to get negative 1/3. Plug 2 in there, we're going to get negative 2/3. But that's not so fun to graph. So what I like to do when there's a fraction that's in front of there, I like to just pick numbers that are multiples of that, right? So like I would start with 3 and say normally when I go over 1, I get to go down 1. But now, make the chart so you can see it. I would pick 3 on this because I know that's when I'm going to get the first whole number. If I plug 3 in there, 3 times negative 1/3 is going to give me negative 1. So I go over 3 3 before I get to go down 1. Do you agree with that? I go back 3, I get to go down 1. So it takes me like 3 times as long to go down what I normally go down at 1. That's what we're doing when we're shrinking this. Which means to go to -2, I think I'd have to go 6. Because 6 times -1/3 is -2. I didn't even make a 6 on here, did I? 1, 2, 3, 4, 5. 6, -2. So a vertical shrink is kind of like, I like the word compression that the Algebra 2 book uses, because it's like pushing down on it, which makes it kind of look like it's wider. Could you see the argument that a vertical shrink, you could argue, was stretching it horizontally? And so that's why, depending on how you see things, if you had to write your own equation, you could write it in different ways, because you could argue that that looks like a horizontal stretch to you, stretching it horizontally. Okay? So you definitely have some graphing on your homework today, but not a ton of graphing. So let's talk about it. 1 through 6. You kind of look at it to make sure you know what you're supposed to be graphing. Sometimes people just assume that all of the homework is graphing because we graphed on the notes today, but the beginning ones just say like describe the transformation, so you don't have to graph those until you get to 21. 21, 22, and 24. It's 3 graphs in 1. Like it's the same, like x21 is all x squared, but there's different transformations. You can make 3 separate graphs. You can put them all on 1 graph, like whatever works for you. But there's 3 graphs for 21, there's 3 graphs for 22, and there's 3 graphs for 24. So one of those is quadratic, cubic, and absolute value. And then I think those are the only graphing ones. The rest are just talking about transformations and then some multiple choice there. So 3 graphs. If you really want graph paper, I can give you graph paper because it really is like 3 graphs on each one. So we make them separately.